Dr. Carlos Vazquez. He received a Bachelor of Engineering and Master of Science degrees in 1992 and 1997 from the ISPJAE Technical University in Havana, Cuba. And he received his PhD degree in Technical Communication from the INRS EMT from Montreal in Canada in 2003. And he's currently Associate Professor at the Software and the IT Engineering Department of the EATS in Montreal. He's involved in 3D TV, 3D vision systems, multi-view video, and 3D object extraction research.
Well, thanks for the introduction. That is a long time ago, 92. So back to now. So I will be talking about geometrically constrained subpixel disparity estimation for stereo images of the retinal fundus. Just to clarify, retinal fundus is the back of the eye. So basically, we put a camera that is going to look inside the eye and then extract the information from the back. This is the work of my postdoctoral fellow, Mohamed Kharboutly, and in collaboration with Stefan Coulombe and Jacques de Guise from the ETS. So my presentation, the outline, a very brief introduction, and then I will be talking about the spherical model of the retinal fundus, how we model that image, and then geometrically constrained subpixel disparity estimation, how we get the subpixel, and then some preliminary simulation experimental results. So this is an ongoing work. We are presenting just very, very preliminary results. So just as a brief introduction, we are doing subpixel disparity estimation of fundus images mainly for view synthesis, for visualization, and for accurate 3D reconstruction. So the fundus images is a well-studied topic in ophthalmology, so there is a very large body of research on that area, mostly dealing with 2D images. So there's a device that is capturing that images for doctors to analyze. There is some work that has been done in 3D reconstruction on the fundus images because there is important structures that you need to see in 3D inside the fundus. So basically, the nerves and the positions of the vessels, the blood vessels, and small structures that could be indicators of disease. So we're interested in knowing what is the depth inside the fundus. So this is our main objective, and so we decided to start looking at stereo images of the fundus. So basically, we have two images captured by two cameras, and then we are extracting the disparity in order to be able to do view synthesis and to generate new views for this for visualization. So the acquisition system, very simple. We are not going very, we are not complexifying this stuff. Just two cameras, pinhole model, a parallel geometry, and we are working with rectified images. So basically, we don't have vertical disparities. We are just looking at horizontal disparities. The first part of the process that we are using is that we are modeling the fundus images. Basically, we are modeling the eye as a sphere. So the back of the eye is is a part of the spheres, and the fundus is the back part of the eye. So basically, we have a camera that is in front of an optical system that will capture the information from the eye. So in fact, we are using a spherical model, which after passing through the optical system can be modeled as quadratic surface in front of the cameras. And this is what is being projected into the two cameras. So by doing some classical, let's say, projection from the spherical, from the quadratic surface where we have our images to the camera planes, we arrive to constraint on the position of the pixel in the left image and the disparity information between the left and the right image. And this is using the quadratic surface that we are using to model this information. So at the end, we have a 7-parameter constraint on the position of the pixel and the disparity that will force or will be used to enforce the spherical shape of the eye. So basically, recovering these 7 parameters is the same as recovering the shape of the global shape of the eye. In that case. And how we are doing that, we are using a feature-based approach in which we are using the characteristics of the fundus image. So there are many vessels, blood vessels inside the retinal fundus, and we are using the intersection of these vessels, or the bifurcation of these vessels, as the feature points that we are using to estimate the parameters of this quadratic surface. So basically, there are 8 parameters that are describing this bifurcation, the Y feature that is called, which is was used for registration of multimodal fluorescent image and sequence of the retina. So this is not. And then we are extracting these features and using the matching of this feature between the 2 images to extract the disparity estimate, the disparity, the sparse disparity information that is used to recover the parameters of the quadratic surface. So basically, we are using a Y feature matching between the 2 images, between the Y features detected in the 2 images, left and right, and then by using the disparity, we get to obtain the parameters that are describing that spherical surface of that quadratic surface that is describing the back of the eye. So from there, then we need to go to a dense disparity estimation, and, because this is just the surface and some points. And for doing that, well, we are doing using enhanced normalized cross correlation feature to do the matching between the 2 images, to extract the correlation between the 2 images to find, to exploit the data, basically, the correlation between the images. The interesting feature of this operator is that by using correlation in pixel positions, we are interpolating the correlation using linear interpolation between the pixels. So this gives us a continuous base correlation, even if we are using just the correlation at pixel base. So basically, we can obtain a correlation metric continuously on the whole image, and this will allow us to compute subpixel accuracy disparity. So this is the main characteristic that we are looking at this operator. So the approach to obtain the disparity, we are doing a global minimization or global optimization approach based on 2 terms energy. A term that is based on the data and is using the previous mentioned correlation operator, and then a term that is based on geometry that will force our disparity estimation or disparity vectors to conform to the shape of the quadratic surface that was previously detected. So for sure, we are interested in detecting or extracting the disparity by, in our case, maximizing that energy. The approach for the maximization, well, I'll get to back later, but basically the data term is based on the operator, the cross-correlation operator, by adding that over the whole image based on pixels, and the data term will be based on the function that is describing the quadratic surface that we defined at the beginning. So basically, we are trying to match the points or match windows between the two images for the data, and trying to match the disparity to the quadratic surface that was detected previously using the Y features. So at the end, this energy is minimized using gradient descent approach. So we are getting to our optimal disparity by looking at the disparity that is maximizing that energy. So the algorithm, just to summarize a little bit, we start by extracting Y features and doing a matching between the two images. From these Y features, a set of these Y features, we are extracting the shape of the surface, the shape of the quadratic surface that is describing the back of the fundus, the retinal fundus. And then from there, well, we obtain these parameters, and then we compute the energy and minimize or maximize that energy to obtain the final disparity map. So to at the end have a dense disparity map that is defined at each pixel. So some experimental results. The first one is using synthetic data. So what we did, we took one original image, we projected that, or we reprojected that back to a spherical surface, and from that spherical surface, we are reprojecting back into the image planes. So basically, in that case, there is nothing else that the spherical surface that is generated, and we're trying to see if our method will recover that. For sure, we have in that case the ground truth of the disparity, because we are generating that disparity, and that ground truth has nothing else than just the spherical information. There is no local variation in that. So from there, we generated the two images, and then from the two images, extracted the Y features. With the from the Y features and the matching of those Y features, we are generating the original surface, and from there we are applying the algorithm to extract the dense disparity estimation. Our results, these results just say that if we don't do the constraining, given that there is information on the used by the data term, where there is no way of, for example, in areas where there is flat areas, textureless, that part of the algorithm is not necessarily working as needed. And by adding some amount of regularization based on the depth, we are getting rid of this variation. So the next step, we tried that with real images. So this is a real stereoscopic image of the fundus. And we extracted manually a set of corresponding points. 23 corresponding points were extracted. And then we apply our algorithms and verified if the disparity obtained by the processing was in correspondence with the disparity obtained manually from these two images. So basically, to get to the subpixel accuracy, what we did after defining the disparity, after extracting the disparity manually, we downsampled the images and applied the algorithm on a downsampled version of the image. So, and we selected points in three different places, close to Y features, texture regions, and textureless regions. So from there, we extracted the Y features, do the matching, applied the algorithm, and finally obtain disparity, a global disparity estimation, or dense disparity. And here we are presenting these are the results for the three categories of pixels. So it's textureless. This is geometric disparity. So this is textureless here. Close to the white features and regions where texture showing effectively that at some points it's better to have the data terms. At some points is the geometric information is being more important. And basically the green line here is the method using the correspondent the two terms in conjunction. So our is this one here. So just to conclude, we apply the spherical model of the fundus and obtain a subpixel accuracy for disparity estimation. And basically now we are looking at localized regularization based on image characteristics, which is suggested by these results here that say that different regions of the image could need different regularization approaches. So thank you very much. This is it, sir.